Let me ask you this question. What exactly is mass? Is it something which is substantial, which is heavy, which is hefty? For thousands of years, we humans have always associated mass with something heavy. But is it true? Or is mass just another form of energy? That we'll see in this video.
Okay, now let's go to the introduction. It's the most famous equation in the physics, E equals to mc², likely because it is easy to remember. Its form is simple and elegant, almost like Nike's swoosh logo. Compared to other physics formulas that more look like Egyptian hieroglyphics, like this one, the Schrödinger equation, this one definitely has a brand appeal. But physics formulas are not just maths, they are supposed to be describing something about physical universe. And this is another reason why E equals to mc² sticks in people's mind. Here E stands for energy, m means mass, and c is the speed of light in vacuum, or 299,792,458 meters per second. To have them all in a simple, easy to remember formula implies that they are connected to one another in a deep and profound way. But what exactly does that mean? How are mass and the energy and light actually related to one another? And what does this relationship say about the fundamental nature of ourselves and the universe? Okay, for most of us, mass is the stuff we are made out of. If something has mass, it generally means it's heavy, it's hefty, it's substantial. We tend to think of things with less mass as lighter, ethereal, or barely there. Now, this is something we developed in our intuition at an early age. It's something that has captured by Newton's laws of motion. For centuries, force equals to mass into acceleration held the top spot as the most important physics equation in the world. In this formula, force, F, that you apply to an object, m is the mass of the object, and a is the acceleration or how quickly the object starts to move. If the object has a lot of mass, then it takes really big force to get the object moving. And if m is small, the gentle push is enough to make it go. To us, mass is measure of substance of something. Things with more mass, like mountains and planets, feel more real and solid. On the other hand, we tend to think of energy as something completely different. We associate energy with heat, light, fire, or motion. Energy feels like something ephemeral that can flow or be transmitted. It gives you power to do things and burn things. Like a magical quantity, it's something you can store or release when needed. For a long time, this intuition about mass and energy fit quite neatly with Newton's laws and basic understanding of the universe. Mass and energy were two different things, although it was clear that they could interact with each other. For example, if you take a cup of water and add some energy to it, like this, then with that energy, the H2O molecules in this water will wiggle a little faster, thereby heating it up. However, the number of water molecules in both the situation should remain the same, and hence the mass should not change with energy given to it. At least that's what we thought. But in the late 1880s, physicists started asking pesky questions like, where does mass actually come from? And what is mass anyway? Initially, they looked at the electron, which had just been discovered. Physicists noticed that when a charged particle, like an electron, moves, it makes a magnetic field. This magnetic field then pushes back on the particle, making it harder to get the particle moving faster. It's the same effect as if the electron had some kind of hard to push mass stuff to it, which gave physicists the first idea that mass and energy, in this case the energy of the magnetic field, could be more than just two different things. Then Einstein stepped in with a clever argument that settled the debate. At the time, Einstein has been preoccupied with the idea of relativity, the study of how laws of physics apply to things that are moving relative to one another. It was known back then that nothing can move faster than the speed of light, and that this speed limit worked no matter how fast you were moving. If you were moving fast, like really fast, you would still see the light moving at the speed of light. This fundamental limitation makes some really strange effects. For example, Einstein considered the case of a rock in space giving off heat. That heat will come off the rock in the form of infrared photons. If you're floating in the space next to rock, you might not notice anything strange. You could see the photons coming off the rock and you would measure that the photons had certain energy, as all photons do. But if you were traveling past Earth at a speeding rocket ship, you would see something different. Einstein used formulas of relativity to figure out that you would see photons coming off a rock at different frequency of light. This is an effect called the relativistic Doppler effect, which is similar to how, for example, a police siren sounds different if the police car is coming towards you or away from you. In this case though, the shift is a little stranger because of relativity rules. Since we cannot see the photons going faster or slower than the speed of light, the net effect is that you, in the spaceship, would measure the energy of the photons to be different than if you measured it when you were floating next to the rock. But since it's the same photon, something else might have changed. According to Einstein, what also changed was the kinetic energy of the rock. But kinetic energy comes from the mass and the velocity of the object. Since the rock's velocity didn't change when it gave off photons, so Einstein concluded that its mass must have changed. In fact, he found that the mass of the rock changed by an amount equal to energy of the photons. What this means is that when a photon leaves the rock, it actually changes the mass of the rock. Now, this change in the mass is the same as if you multiplied it by the speed of light squared as the energy of photons emitted. It seems that a little bit of mass of the rock was transformed into energy, which then went off in the form of photons. Remember that photons don't have any mass, they're pure energy. This was pretty groundbreaking thing. Thousands of years of human intuition was thrown out that said that energy and mass were totally different things. What Einstein equation showed that mass and energy were related and can be exchanged with each other. It's like you can go into a currency exchange store and trade euros with dollars and dollars with euros. At this point, you might be wondering, what does this mean? How exactly can something like mass, which has substance, be transformed into pure energy and vice versa? Initially, you might think that a few of rock's atoms somehow disintegrated and became these photons. That would be one way for the mass of the whole rock to decrease, but actually this is not what happens at all. The rock has same number of atoms before and after the photon is created, but somehow the mass of rock decreases. This is very strange to us because we are not used to mass of things changing. If you have a metal weight at your desk, you don't expect the weight to be lighter or heavier just because you turn the air conditioning on or off. A kg of sugar is still a kg of sugar regardless of whether you have put it in the fridge or you have kept it outside, right? So what's really going on here? To understand this, we have to dig a little deeper into what it means for something to have mass. In particular, there are two important clues that will help us put this puzzle together. You probably think of yourself as being made of solid stuff. After all, you are what you eat, and you eat stuff, not lightning or sunbeams. When you poke your finger against your arm, it feels pretty solid. But actually, if you look closer and zoom into the bits that make you up, you will see that there is really not much in there at all. If you look at any particular atom in your body, a lot of it is empty space. Almost all of the mass of the atom is found in the nucleus, since protons and neutrons each weigh 2000 times as much as an electron. Even more fascinating is that when you crack open a proton or a neutron, you'll find that they're actually made of up and down quarks. 2 up quarks and a down quark for proton, and 2 down quark and an up quark for neutron. So really, most of your mass in your body is in those group of quarks. Nothing interesting there. But what's really interesting is what happens when you separate those quarks. Assume that these 3 balls are quarks and the bond between them are gluons, making sure that they are connected to each other. Effectively, this is proton. Now, if I take this proton and weigh it in the weighing machine, I should see its weight about 10 electron volts. But if I separate these, like remove these gluons, which are basically nothing but energy, if I remove these gluons and take measurement of these quarks individually, you'll find that together they make only 1% of the total weight, and this energy accounts for rest 99%. Now, these quarks hardly have any mass by themselves. They each weigh less than 1% of the mass of proton. And yet, when you put these quarks together, somehow their mass increases by a factor of 100. That's like putting 3 Lego pieces together and finding that all of a sudden they weigh as much as 300 Lego pieces. What's going on? Where does all this mass come from? The surprising answer is that the mass comes from energy that ties the quarks together. You see, one amazing fact we have learned is that energy acts like mass. If you have a bit of energy in one spot, say trapped in the bonds between two particles, that little bit of energy will be hard to push and pull in the same way that mass is hard to push and pull. If you separate two particles and let the energy dissipate, then particles will be easier to move around. Or in simpler words, energy itself has inertia. Not only that, energy also feels gravity. Any little bit of trapped energy will also bend space and get attracted by other objects, just like things with mass do. In simpler terms, if these 3 quarks along with these gluons, the bond between the quarks, if they account for 100 grams, which is the mass of a proton, for example, then individually these quarks together will make just 1 gram, and rest 99 grams will be from this, and these are nothing but energy. So most of the mass is coming from energy, not solid stuff as we think. If you were to split llama in two, the sum of the masses of two pieces would be less than the mass of original llama. And how do you figure out what's the equivalent energy of that lost mass is? You guessed it, E equals to mc². Now that's partly what E equals to mc² means. The mass is equivalent to energy, and it turns out that most of what we consider to be our mass, about 99%, is actually just energy. What about the other 1% of us? That's still stuff, right? Actually, not so much. In last 100 years, we have also learned a lot about nature of the mass of the fundamental particles. The physicists have looked as closely as they can, and so far, particles like quarks and the electrons don't look like they are made of smaller pieces. This tells us that their mass doesn't come from the energy holding smaller bits together. So where does their mass come from? The original idea from 1880s was actually on the right track. Electrons are harder to move because of the magnetic field that they generate. But there's another field out there that also pushes back at them, the Higgs field. Filling the universe, this quantum field tugs at all of the matter particles, making them harder to move. This is where the mass of each particle comes from. But that's only the partial explanation. The full explanation is that the mass comes from energy of Higgs field. Some particles interact a lot with the energy stored in the Higgs field, which makes them harder to move. And some particles have weaker interaction, making them easier to move. In other words, the mass of each particle is really just the strength of the connection to the energy of Higgs field. And we can go a step further still. According to quantum theory, quarks and electrons themselves are nothing more than little ripples of energy in quantum fields that permeate the universe. A particle is just a burst of energy, same way that a shout is a ripple in the air or an ocean wave is a ripple in water. In other words, even the particles themselves are just energy. So what's the massive conclusion here? Both of these clues, that most of the mass of an object is the energy of the bonds that hold that object together, and that even the mass of each particle is really just energy, leads us to one amazing and somewhat shocking conclusion. What we thought of as a mass doesn't really exist. It's all just energy. This is how a rock in space is able to lose mass when it radiates a photon. It doesn't lose mass because it transformed matter into energy. All matter is already energy. So the rock just transformed energy from one form to another. In this case, it transformed the energy in the motion or vibration of molecules into a photon. So when you think of a rock in space, don't think of it having mass and energy. Just think of it as one big blob of collected energy. Some of that energy is in particles, some of it is in the bonds of the particle, and some of it is in the motion of the particles, but just one pool of energy. And that is why in E equals to mc², one form of energy is really translated into another form of energy. The famous formula does tell us that there's a deep connection between mass and energy, but it's not that mass is something that can be transformed into energy. What we have learned is that all mass is just energy. It's energy of the particles of an object, either their bonds with one another or in their interaction with the Higgs field. The idea that energy has inertia or it weighs something feels odd and counterintuitive, but that's only because we have been thinking about mass the wrong way for hundreds of years. There's no such thing as stuff. It's only energy and the impact it has on the shape of space and how things move. Those are the two sides of Einstein's two-part relativity tango. Thanks for watching.